So folks, we're picking up our videos on this technique of separation of variables. In the last one, we went ahead and actually took a separable equation and we separated the variables by dividing y over to one side and multiplying differential x over to the other side. So the first thing, of course, to say is that you cannot always do this technique. It only applies to the classification of ODEs called separable ODEs. Separable ODEs, and we'll define that here in just a second. The other thing to be very careful of is that this technique generally does not find all solutions to an ODE, and in fact sometimes we will have what are called singular solutions to an ODE which are not found by performing the technique that we did in separation of variables here, and we'll talk about why that goes awry in one of our examples. Before we do that, let's go ahead and just define the term separable. So a first order ODE, so this applies, I'm only applying it to first order ODEs, it's said to be separable if it can be written in the form, and here I'll use y as the dependent and x as the independent, so dy dx is equal to, and I use the letters g, so g of x times h of x. So if you, h of y, that's a huge mistake, folks. Let me highlight that mistake in red. So if you're able to write this as a product of two functions, one a function of x and one a function of y, then that means you've got a separable equation at hand, and the technique of separation of variables may apply, and it may be the best route to take in solving the ODE. So let me just say that again. This is any first order ODE that can be written in normal form, looks like this. But if we can write it as a product, that's what we've done here, right? We've written it as a product of a function of x and a function of y, then we would call that ODE separable. So I claim that this ODE right here in number 6 is an example of a separable ODE. Let's go ahead and identify the two functions, the g of x and the h of y, that form the product. So let's see what we can do here. To be separable, we have to write it as a product of a function of x and a function of y. So let's see what we can do here. Well, certainly I've got a factor of x here. Here's a factor that depends, or excuse me, here's a factor that depends upon x. Here's a factor that depends on y. The other thing I can do is, using my properties of exponents, I could rewrite this as e to the 3x times e to the negative 2y. So then what I'll do is we'll just regroup things through the commutative and associative properties, and so we'll say that dy dx is equal to this. Let's go ahead and write e first. So we'll say e to the 3x times the sine of x, all of that, times y e to the minus 2y. So here it's clear that we've written this differential equation. We've got dy dx on the left hand side, and here we've got an expression just involving x and an expression just involving y, and so the g of x then would just be e to the 3x sine x, and then the h of y would just be the y e to the minus 2y. Because we were able to write it in this separable form, this is a separable equation, and the technique that I showed in the first example would apply. So let's keep working. This equation here in number 7 is not an example of a separable equation. That is, try as you like. If you isolate the dy dt term, put it into normal form, you would have t minus y. There's no way to write this as both a factor of as a product of two factors, one of x and one of y, and so that's not separable.